to our 30th meetup of KW Intersections. And today we will have two talks. First talk will be by Ivas Kabir, and we'll talk about modern SAT solvers.
Thank you very much. Thanks everyone for coming. I'm going to start by talking about myself. I love talking about myself. So firstly, I'm a graduate student at the University of Waterloo. I did my undergrad there too. I did my undergrad in pure math and computer science, and now I decided to focus on computer science for my master's. So I work in the programming languages group. And most of my current research focuses on, well, there's a weird link, sorry. Scala and the dot calculus for Scala, which is formalization of like the core. It's a calculus that like models the core like ideas in Scala, and I guess like our research group works on like trying to extend the dot calculus to like the full Scala language. And I also am currently working on a toy language that uses linear types to like try and add pointers to functional languages. So that's me. Let's move on to SAT solvers, and I'm going to begin with like talking about the problem itself. So the SAT problem is given a Boolean formula, such as this one. Can we find an assignment to the variable such that this formula evaluates to true? And we say that a formula is SAT if there is such an assignment, or unsat if it's if no such assignment exists. So an example would be if we assign A to true, B to false, C to true, and D to true, then this formula, the above formula, evaluates to true. And switch over a little bit. And this ends up being a very hard problem to solve. It's one of the classical NP-complete problems. So what does that mean? That just means that assuming that P is not NP, which is, I don't know if you don't know what those are, some like believable assumption. Like solving SAT will take exponential time, assuming that this like weird assumption is true. And a lot of people believe that assumption. So there's intuitively understanding that like, oh, the best algorithm we can write to solve the SAT problem is going to take exponential time. So does that mean there can never be an efficient algorithm for SAT? No, there can't be. You'll always find a formula such that it will take exponential time on your algorithm. But we can kind of like work around that by saying that, well, in the worst case, there will be such a formula, but for most of the cases you care about, you might be able to find an algorithm that performs like well enough. Going off that, let's talk about some background. We say that a formula is valid or true if it evaluates to true under all assignments. And normally, SAT doesn't really tell us, like, if a formula is satisfiable, it doesn't mean it's true, or like, so like SAT doesn't really tell us anything about if something is valid or true. But if a formula is unsat, then its negation is valid. So if a formula is unsat, then it evaluates to false under all assignments, and hence its negation evaluates to true under under all assignments, and hence the negation is valid. And I also have a definition here that I didn't really know where else to put it, but a literal is a variable or the negation of a variable. We'll meet that later. Any questions so far? Yes. Okay. So more background. We say that a formula over some variables is equivalent to another formula over the same variables if for all assignments to those variables, the first formula is true if and only if the second formula is true. Well, where did I go? Okay, for example, A is equivalent to not of A. This like, maybe you shouldn't use the space button. Okay. And I was using up, down, and like left, right was really close, and they would just jump. So similarly, we say that a formula is equisatisfiable to another formula over the same variables plus some more if the first one is satisfiable, if and only if the second one is satisfiable. Okay. So those are formulas, and now we want to talk about like normal forms. So it's very hard to like think about how to solve the SAT problem if we have just any formula, and we want to like, where did that go? Oh, I had an example. Like, if I have a formula and the same formula together with any other satisfiable formula, then they're equisatisfiable. It's easier to try to come up with algorithms for solving a problem if the instances are in some sort of a normal form. And for Boolean formulas, the two like well-known normal forms are disjunctive normal form DNF and conjunctive normal form CNF. And the disjunctive normal form is an or of ands of literals. So like there are like ors in between, and like, inside these clauses there are ands. And a literal again is a variable or its negation to the negation. Okay. And conjunctive normal form is similar, except the ors and ands are flipped. And so we can convert any Boolean formula into an equivalent CNF or DNF formula using the De Morgan's law and eliminating double negations. These are the De Morgan's law. Not of A and B is equivalent to not A or not B, and similarly with not of A or B being equivalent to not A and not B. But and like we can naively apply De Morgan's law over and over again to convert any formula into an equivalent CNF or DNF formula, but it leads to a what happened again? Where did we go? No, this is too far. Okay, it leads to an exponential blow up. Like if we start off with like a very small formula, if we naively apply De Morgan's law, it'll grow up to a huge one. But if we give up on like the idea of equivalence and settle for equisatisfiable, we can do better. And the process for doing this is called Satin encoding. And if you guys are from an electrical background, you may know that this is how you convert a Boolean formula into a circuit. So we start off by given a formula f. We let S of f be the set of all subformula for f. And then for every subformula, we introduce a new variable p sub g. And then the Satin encoding is defined as follows. If f is a literal, then we just let the Satin encoding to be p sub l and CNF of p sub l if and only if L. Or the L's don't show up properly. And this is like naive De Morgan's CNF here. You can convert it back to like, a CNF formula. And then if it's of the form G and G2, then we just let P sub f, the Satin encoding be P sub f, and for every G of the form G1 times G2, not times, but like some operator applied to G2, then CNF of P sub G if and only if P sub G1 operator of P sub G2. Any questions so far? And this converts a formula to CNF formula with only a linear blow up in the size of the formula. And you can see the linearity kind of by saying that these two parts have a maximum size, say C, and then we only do this like linear number of times based on a formula can have only a linear number of operators. So if you do it only a linear number of times, you only have like C times the size of the formula.
Sorry, I have a question.
Yeah.
The if and only if and the implication, are they considered operators in the original set problem?
Yeah. So if and only if is just if and then and together with only if, so you can convert that back down to. I don't know if that explains the question.
So you can use those intermediately and then you reduce them again.
Yeah. But like either way, it'll just be a linear size. So that was the mean. So now we can kind of like assume that everything is in our inputs are in C and F, so that makes our problem a little easier. And then I want to talk about like Boolean constant propagation, which is the process of taking simplifying certain Boolean formulas. So suppose we have this following formula. This lonely A here, for us to have any hope of this formula being formula evaluating to true, we must assign true to A. So this forces assignment A true. And then after we assign this to true, we can kind of like get rid of it. And since we've assigned A to true, we can get rid of anything that contains an A. So we can cross those out. And all the negations of A, we can kind of like remove as well because they don't contribute to the truthness of this formula anymore. So we're left with C and negation of C or D here. And this again forces an assignment of C to true. And we can keep going like this, and then this forces the assignment of D to true, and then this formula is therefore satisfiable. So in this example, we were able to like go all the way to true, but sometimes you might end up with like only not having any like of these like low literals anymore. So at that point, you kind of get stuck. But the like interesting thing about this is this process is polynomial time. It's a very efficient process of simplifying way of simplifying a Boolean formula, and I think like this naive approach is like n squared time, but you can do even better. So this is known as Boolean constant propagation, and as I said, it can get stuck. But like this kind of leads to our first SAT solving algorithm. Just switch over pages in my notes. Okay, let's study this a little bit. So as we saw, BCP takes a formula. Oops, that's an extra one that shouldn't be there. And returns a simplified formula. We'll also need a way of choosing a variable of a formula and assigning a variable of a formula to some Boolean true or false. So this gives us, I don't know if you guys are familiar with OCaml syntax or not, but so this is kind of a little weird if you're not familiar, but it's just, I'm calling this function isSat, and it takes in a formula phi, and it performs BCP on phi. And then if BCP returns true or false, we know that the formula is either satisfiable or not satisfiable. And otherwise, we choose a random variable, not necessarily random, but it can be random, from the BCP formula. And then we make an assignment to that variable. We start off with setting it to true. And if that returns that, if that returns true, then we say that this formula is satisfiable. Otherwise, we try again by setting it to false. And we recursively call isSat on the, after assigning x to false. And this is known as the DPLL algorithm, and it was introduced in the 60s. And it was state of the art until early 90s. And since then, we've made some improvements to this DPLL algorithm that make it like a little faster, or way faster in certain cases.
Is there a simple example of a formula for which this takes exponential time?
Yes, I'll get to that later. And I won't give you a simple example. I'll give you an entire class of problems that it'll take exponential time. But so far it looks really efficient, right? If BCP is performing really well, it'll perform really well. Is there a question?
Basically, constructing a decision tree.
Yes, we are constructing a decision tree.
So ideally, you'll have to traverse the whole tree to the end.
I can't hear you. You have to speak up a little.
You'll have to traverse the whole tree in the worst case and 2 to the n nodes.
Yeah, in the worst case, you like search the whole tree and make every possible assignment. But because of BCP, you expect to like kind of like prune the search tree early on enough that you don't have to go deep into it to like get either SAT or unsat.
Are there smart, intelligent ways to choose the variable lengths?
Yes, there are some like smart ways of choosing a variable. But I'll get to that later. So we'll see that later. But before we go on, I want to cover cover some of the hacks we do to like improve upon this algorithm. So I need to cover a little bit more background. So if a formula implies another formula, phi implies C, then we know that phi is equisatisfiable to phi and C. And let me switch over my notes. So when we assign like x to true, if this is unsatisfiable, we learn something. We learn that yes, this is okay. We learn that C implies not of like C with the like x assigned to true. So like we've kind of like learned something, and we can try and abuse this knowledge. Let's move on a little. But like this formula is too large to add to like phi itself. Like if we naively do this, we just double the size of our formula. But we have this like notion of an unsatisfiable core of a formula for an unsatisfiable formula. And so we can learn like a very small clause that still tells us something. Was there a question? I won't go too deep into it, but clause learning is a complicated process. But like it gives us better gains on BCP because now we have like more possible literals around that, like, and possibly some of them are lone, or some of them are short enough that after you make an assignment, it produces a lone literal. So like it makes BCP performing even better. Is that all I have on this slide? Yeah, and this class of solvers that use clause learning is called CDCL solvers. And CDCL stands for conflict-driven clause learning. So that's all I have on like basic SAT solvers, at least. So I want to like take a detour into like what we use SAT solvers for. So firstly, we use SAT solvers to solve the SAT problem. But like there's some other applications too. We often solve graph isomorphism using SAT solvers. So given two graphs, with like weird edges going between, I don't know. Given two graphs, if you want to like see if they're isomorphic or not, we just convert this problem down into a SAT problem, and then we solve it. And our SAT solvers perform really well, so we can pretty easily tell whether two things are isomorphic or not, or at least on most graphs. There are some graphs that will like take exponential time again on this. And we also use SAT solvers as a part of SMT solvers. And SMT stands for SAT modulo theory. So we can combine a SAT solver with a solver for another theory, such as like theory of integers or something, and then we can solve things like, oh, can we assign x and y integers to x and y such that this holds true, or is this unsat as well? And SMT solvers are used for concolic testing. So that's given a piece of code, we can see if like assertions can be violated in that code or not. So for example, in this, I guess C or C++ code, like if we go down this branch of like x is greater than y plus 10, can this assertion that x is less than y ever fail? Like it'll give you values of x and y such that it fails on if it does find such a thing. And like string solvers are used for like web apps to test for SQL injections, for example. Like that's another application of concolic testing. I think that's all. And this is the example of a class of problems where SAS solvers take the whole time. So if we take the question of given n holes and n plus 1 pigeons, can we assign holes to pigeons such that each hole only has one pigeon in it? And from like mathematics, we know that this is like, no, we can't. This is unsat, but if we convert this problem to an instance of SAT and give it to a SAT solver, it'll take the entire exponential time before returning unsat. Some more slides left. Okay. And so that's like a class of problems that we can't solve, but I want to go back to CDCL solvers a little bit and talk about some heuristics that like make CDCL solvers perform even better. We go back to this like variable choosing, and so if a variable like shows up in the clauses you're learning a lot of times, then it means that assigning to it like can like suddenly give you more lone literals for BCP. So that's one thing that we do. Like we have different strategies for like choosing which variable is like in some sense showing up in a lot of learned clauses, and then we assign to that variable to make BCP perform better. Another hack that we do is clause deletion. If we're learning too many clauses, it's like making our problem even like longer, right? So and like our clause database gets large, so we sometimes just randomly, not really randomly, like delete unhelpful clauses. Like if we are not assigning anything in a clause for a very long time, then we kind of just say, oh, this is not being useful for the next little while, so we'll just delete it, and when we need it, we'll learn it again. So we can just do it. Another thing that we do is restarts, and so this is when like you're deep in the search tree and you keep making assignments and they keep being unsatisfiable because you're not assigning a variable early enough in the search tree. So we just randomly restart sometimes after learning enough clauses, so that we make these assignments earlier on, so that like we kind of go to either SAT or like a satisfiable instance earlier on. And that's the end of my talk. Thank you for coming. Any questions? You can go first.
So about the heuristics for choosing a single variable assignment. So it's something like maybe the number of times it appears in all the clauses or something. Are there any heuristics for, say, in the tree, choosing a joint assignment, say, choose 3 or 4 variables and assign them simultaneously?
No, just because like early on these.
Or would it? You would still have to try. So because you would have to have 8 sub-trees.
So we can only assign like one at a time, right? Like if we have like a clause like A or B and we make an assignment to A, through BCP it'll automatically make an assignment to B, right?
I
So
see.
that's why we don't really need to make joint like.
So it doesn't save you anything.
No.
Are there ever a couple different heuristics that all, so like this one has these kinds of optimal cases and these kinds of drawbacks, and these ones have these kinds of optimal cases and these kinds of drawbacks, and you just kind of like try a couple to a shallow level to see if you get any early wins with trying to cover like easy ground or something?
So there are SAT compositions, and like people like throw their solvers at like huge instances, and like so there is a SAT solver that will like statistically say that I look at this like formula and then I try and judge which solver to use, and then try and use that solver, and if that solver is taking a lot of time, we look at the learned classes and try and choose another solver. And this solver is banned in SAT competition. Because you're in some sense cheating. You're throwing all possible SAT solvers at the problem rather than improving one. So I think
So it's effective then?
it is very effective.
If you have to ban it, you know it's the good one.
Any other questions?
Is there any work on SAT for logics other than classical propositional logic?
So SAT is
Yeah, it's
classical.
the analogous problem. I mean,
Yeah, but like we can have like SMT solvers for like not necessarily like full first order, but other logics. So like we can combine like the Boolean world with like integers and like solve for integers. So like similarly we can do for like strings and some other logics. So.
But not like say if I want like you mentioned linear types, so like a linear logic, right, which is not. It may not have double negation depending on my system, and it's not. People are not really doing this. Or?
I haven't seen anything, but like I'm very new to the world of SAS solvers myself, so like maybe someone else. Like you'd have to look it up.
I believe.
You mentioned that one of the things that the SAT solvers are used for is graph isomorphism. But given that it's an NP complete problem, could in theory, like are there other NP problems that even though you can turn them into SATs, it's like SAT solvers are just garbage at, or is it like kind of any NP complete problem could be used with a SAT solver effectively?
So a lot of NP complete problems, when you convert between them, they incur polynomial overhead. And that polynomial overhead can be large enough that converting to SAT does not really help you.
Okay.
So if it's like n to the 5 like overhead, then like there's no point in trying to solve this. I had another question back there.
And I want to add something to that.
Okay.
Usually, as far as I've seen, instead of using SAT solvers, they usually convert these formulas into linear programs or something else and try to go simplex or some other.
Right.
And also graph isomorphism is not incomplete.
Isn't it?
It's one of those ones that we don't know.
Oh, okay. My bad.
My question was, do you have any other examples of like heuristics used for the restart part? We mentioned like the banned SAT solver. Well, it was taking a while, but besides that.
So for restarts, one of the more common ones is every 128 learned clauses you restart. But one of the ones that have been gaining popularity is try and restart geometrically. So after like 2 learned clauses you restart, and then after 4 learned clauses you restart, then again after 8 learned clauses, and so on. And one of the things with restarts and clause deletions is if you don't do this in like a sane enough way, you can loop forever. Because you just deleted a clause and then you restart it, you relearn the same clause, and you keep doing this. So if you're not careful, you can loop forever. So these kind of geometric restarts help with that too, because it makes sure that you at least complete the search tree at some point. Yeah. Any other questions? Awesome. Thank you for hearing me like blab on for a bit. Thank you.
Yeah, it was the filters that it is, what's important, what's not important.